Hello, and welcome to this next lesson on high level mathematics. So we're moving on to a new uh, section today on moving on from numbers onto ratio and proportionality. So a small section this, we're just looking at how to calculate with ratios and proportions, and then how we apply those, which we next lesson. So let's take a look at the lesson plan. So we're looking at what ratio is, how what ratio is like as in a proportion, how we can use ratio to share some quantity in, say, an uneven way. We'll take a look at that. How to take a proportion. So if I've got, you know, a particular quantity and I want to take some proportion of that, 43%, for example. What is 43% is quantity? We'll look at how that works. And then we're looking on to a sort of different but related topic known as proportionality, which is describing sort of how different quantities are related to one another. Direct proportionality, when they go up together. Inverse proportionality is when, as one goes up, the other one goes down. We'll take a closer look at how that works. So first of all, ratio is proportion. So ratio is a mathematical expression that shows relative amounts, and that's important. It's relative amounts. So it's not actually how much we have of one thing and another thing. It's how much we have of one thing relative to another thing. And we'll see how that works with this little example here. So say if I've got 6 apples and 9 oranges, the ratio would be 2 to 3. And the reason why that would be is because we can group them up like this into a number of groups. It doesn't matter how many groups, but within each group, we can see there are 2 apples and 3 oranges. And so that shows you the relative amount of each quantity. We don't actually have 2 apples and 3 oranges. We've got 6 and 9. But we know for every 2 apples, we have 3 oranges. Is that relative amount is what's important. And yeah, so ratios are useful for many different things, in our day-to-day lives, like cooking recipes, um, but also in the work. Like say if you're working as an architect, for example, and you've got to look at map models, and we have a ratio of the size of the map compared to the building in real life, and things like that. That's another example of ratio. Right, so ratios are usually expressed using smallest whole numbers we can use. So very similar to how we do with fractions, and we want to then simplify those fractions by making numbers smaller. And we do that similarly with um, ratios. So say here we have 6 to 2, and that 6 to 2 could represent, say, something like this, like on a you know a lot, selling vehicles, and you might have 6 cars and 2 motorcycles like that. However, that's not the simplest ratio, because you see that number, that ratio there, um, where you have 6 cars for every 2 motorcycles. You see how we can break that down further to actually have 3 cars for every 1 motorcycle. And so what we can do is we can get rid of one half of it, and it actually can be reduced down to just 3 to 1. That would be an equivalent ratio. So that's a way of visualizing what's going on there. But mathematically, it's kind of like the same as with fractions, where if we multiply or divide the numerator and denominator of a fraction by the same number, the ratio doesn't change. The fraction doesn't change. And it's the same thing here with ratio. If we multiply or divide both sides of the ratio by the same number, it doesn't change the ratio. So, we can do that in both directions. So, say for something like this, where if we have fractional or decimal numbers within our ratio, and maybe we want to get to whole numbers, we can use this technique we have for manipulating ratios to get that. So say for something like this could be like the efficiency of a car that uses 1 liter of fuel for every 11.4 kilometers it drives. Well, what we could do, we could multiply both sides by 10 to get 114 kilometers for every 10 liters, and then simplify those numbers by looking for the common factors again. In this case, we see a common factor of 2. We can divide the 114 by 2 to get 57, the 10 by 2 to get 5. And so we've managed to manipulate that ratio there to get the smallest whole numbers that we can, if we wanted to do that, or we could go vice versa. This is how we work with ratios. So, um, this concept of ratio can be extended to three or more things. Like say this example here I have for a recipe. So this little recipe for say a flapjack, it's got oats, syrup, butter, and it makes for four people. So we can make a ratio between these items by simply putting the numbers together. So if we wanted to express this mathematically, it would just be 500 to 350 to 150. Each number, that you've got to be mindful of what each number is representing. The first one being oats, the next one being syrup, the next one being butter. And then we could simplify that ratio if we wanted by dividing each number by 10. Then we can see a common factor of 5, and we get this ratio of 10 to 7 to 3. So that means, for every 10 of the oats, we're getting 7 of the syrup and 3 of the butter. Be mindful that each one has its own unit as well. Here we've got a mixture of units, grams and milliliters. The ratio doesn't care about the units. It just cares about like the numerical values and the relationship between those, like the relative amounts. So say if instead we had 750 grams of oats and we wanted to make flapjacks out of that using this recipe, okay, what we have to do is try and work out how would we have to adjust the other recipe, ingredients, so that it's still going to come out right. So what we can do here, like you see in that final ratio, 10 to 7 to 3. So we see this 750 represents 10 parts in this ratio. And we're going to take a look in a sec what exactly I mean by parts, this concept of parts. But you see it represents 10 parts. So one part is going to be 75 grams. Well, once we know that, we can then know how to adjust the others to ensure that we get the correct combination of ingredients. So we know one part represents 75 now. 75 grams for oats, but like I said, it doesn't care about units. So it's going to be 75 milliliters for syrup. So what we do is you times that by 7, because in the ratio you see it represents 7 parts. And then finally the butter that represents 3 parts. We do 3 lots of 75 and we get 225. So if we can calculate what one part is there, we can then work out how to adjust the other values based on that ratio. So let's take a look at sharing by ratio, where this concept of parts of a ratio will make more sense. So let's look at that ratio again of 2 to 7 to 3. So in total there's a total of 20 parts. 10 parts oat, 7 parts syrup, 3 parts butter. 10 plus 7 plus 3 comes up to 20. So you could think of this as just like here, like a rectangle which represents your total amount of stuff. And what we're doing is we're dividing it up into 20 parts like that. And then you imagine dividing it, or like splitting up that quantity into 3 parts, but not 3 equal parts. And so here you see the first has 10 parts, the second has 7 parts, and then the final part is just made up of 3. And so if we wanted to put this as, say, a fraction, we would have this, the first part of the ratio is 10 out of the total of 20. The next one is 7 out of the total of 20. The final one is 3 out of the total of 20. So this gives us a way of converting from ratio to fractions. Because say if we want to actually share some quantity by a ratio is kind of similar to percentages, like I mentioned in previous lesson. It's kind of always more for demonstration purposes, but it's hard to do direct calculations with ratio. We generally need to convert to, say, a fraction like this first. So that 10 over 20, you see, we can simplify it to a half. Now, so say if we're trying to share some quantity based on this ratio, I could give you an example here, like say 120 pounds, I'm splitting amongst 3 people using this ratio. So it's like you're trying to divide something up in an uneven way. Because if we're dividing up evenly, we could just do 120 divided by 3. And there we go. Each person gets 40 pounds each. But say if this is like part of a business, and maybe they each own the business in different amounts. Maybe they've each invested different amounts into that business, and they have this split of 10 to 7 to 3. And so the profits of this business, they want to split by that same ratio. That's one example of why you might do this. Well, then once we've got these fractions, we can know how to calculate each person's amount. So the first person is going to get half, which is 60. The next person would get 7/20, which comes out to 42. And the final person would get 3/20, which comes out to 18. So that's why we want to calculate fractions, like to turn a ratio into a fraction. If we're trying to actually split something up based on some ratio like this, that's typically why we want to do that. So you see here where I'm taking a proportion of the 120. Let's look a bit more into that. Like, how do we actually take proportions of a quantity? So, say, for example, if we're trying to take 45% of 160, again, like I just mentioned, you can't really do calculations so much with a percentage. What we want to do is convert it to, say, a fraction first. And so we're trying to do 45 over 100 times by 160. That's how we can take a fraction of some quantity if we multiply it. So when we multiply by a whole number like that, the whole number is going to essentially join on the numerator there. So you're going to get 65 times 160 over 100. Now, to simplify something like this, we're going to have to try and look for common factors. And really, you don't want to have to multiply 45 by 160 unless you've got a calculator. If you've got a calculator, you could just plug this in and it'll work it out. But say if you didn't, you don't want to work, do 45 times 160 because it's going to come up to quite a big number. What we want to do is instead, like what we did in the prime numbers class, is try and break things down into their common factors and find common factors between the numerator and the denominator. Here, you see I've broken up the 45 into 5 times 9, the 160 into 20 times 8. And now we've got a common factor of 5 and 20 on the top and bottom, which we can cancel out. And we get 9 times 8, which is 72. Because you're doing 5 divided by 5, 20 divided by 20, they're just going to cancel out. We can do a similar thing here. So 0.2% of 12,000 is going to be like 2 1,000ths of 12,000. The reason why that is because, again, percentage per 100, we basically got 0.2 out of 100. So 0.2 divided by 100. Now, we don't really want a decimal in our fraction, so what we do is times the top and bottom by 10, and we get 2 out of 1,000 instead. So we're basically doing 12,000 times 2 divided by 1,000. Well, the 1,000, 12,000 over 1,000 is going to be 12, so we get 2 times 12, 24. So let's look at like a reverse scenario here. So a car has been discounted by 15% in a sale, and its new price is this, £6,375. And we're trying to work out the original value. So in these kinds of scenarios, you don't really want to work out like the 15% and then try and deduct it from the original value or add it back to the value or anything like that. The best thing to do is to think of it in that we had 100% of the value before, and now it's been discounted 15%. So we've taken 15% away. So what we're left with is 85%. So therefore, this you can kind of see it like this: like 85% of the value of the car is equal to 6,375. So this is almost like an equation. If you've encountered algebra yet, we're going to be moving on to that soon. Algebra can certainly come in use here, but you can kind of this one's simple enough that you can kind of just think about logically. So we know 85% of the car, so it's basically 85 over 100. That fraction times by the value of the car is getting us this 6,375. So if we try and do the reverse of that, so the car is then going to be 6,375 divided by 85 over 100. That's going to essentially undo that operation. And so again, if you've got a calculator, you can just plug that in. If not, then you might need, it probably wouldn't be a scenario like this. You might get something with nicer numbers. If you're dividing by that fraction, remember it'd be the same thing as times in by the reciprocal. So it'd be like times in by 100 over 85. And you'd have to just work it from there. Typically, these kinds of questions, it'll be calculator-based questions. Right. So let's return to that example we had before, like with the recipe for flapjacks. Very practical life skill. So if you see at the bottom, we said this makes for 4 people. Now, say if we wanted to work out how many ingredients we'd need for 6 people, how would we do something like that? So what we need to do is try and find the scale factor that takes us up from 4 to 6. Like, what do we have to multiply 4 by to get to 6? And if it was a number like 8 or 12, it would be quite straightforward. You just times by 2 or 3 or whatever, but 6 is not so easy. You might be able to see this. It's going to be 1.5. Like 4 times 1.5 gets us to 6. because half of 4 is 2. 4 plus 2 gets you to 6. But for a general case, like say if you've got any two numbers, how can we do that? Is by observing something like this. Like say if we're trying to get to 6, we start with 4. What we can do is we can take that 4, divide it by 4, it'll get to 1, and then times it by 6, it'll get it up to 6. And we could do that with any two numbers. Like say if I divide a number by itself, it'll get to 1. And then I could times that by anything I want, and it'll get it up to that number that I want. And if we put those two operations together, you can then find out what that scale factor is. So if we're dividing by 4 and then multiplying by 6, that's the same thing as multiplying by 6 over 4. And 6 over 4 can be simplified to 3 over 2, which you might recognize as 1.5. So that's how we can find a scale factor for any two numbers. If we want to go from one number to the next, okay, divide that number by itself and then times it by the number you want. And you see it's going to take it down to 1 and then up to the number you want every single time, no matter what two numbers you pick. So that's a really handy technique to find out what that scale factor is from one number to another. And once you've got that, that's the hard part. Then you've just simply got to apply that scale factor to all your values. So we basically need 1.5 lots of these ingredients. So we have 750, 525, and 225 grams. Well, actually, that middle one should be milliliters, but the numbers still work out the same. And you might recognize those are the same numbers we had before. So, right, let's move on to proportionality now. So this is related to ratios in terms of that they're related to proportions, but it's a little bit different. So let's look first at direct proportionality. So what that means is that when it's a relationship between two different quantities, and then as one goes up, the other one goes up too. So a simple example would be something like this: like say if I'm making one, I'm selling some product and I'm making £1 per sale. I would then earn £100 for 100 sales. If I only make 50 sales, I'm going to get £50. The more sales I make, the more money I make, and they go up and down in perfect lockstep, which is what you would expect. But they won't always go up and down by the same amount. Like, say, if we have an example like this, if I'm traveling at 60 kilometers an hour for half an hour, I'll travel 30 kilometers. If I travel 30 kilometers an hour for only half an hour, then I'll travel 15 kilometers. So you see, as I've gone down by 30 in terms of speed, I've gone down in 15 in terms of distance. So it's not the same number, but it is the same scale factor. And that's what we're looking at here. Like 60 down to 30, it's halved. 30 down to 15, it's halved as well. But again, you see they're going up. So the exact number won't necessarily be the same, but it's still going up and down. As one goes up, the other one goes up. As one goes down, the other one goes down. And then there's some cases where they won't even go up or down by the same rate either. And that'd be, say, something like if we're looking at area. So say if we have a 1 by 1 square like this, the area is 1 centimeter squared. If it's 1 centimeter by 1 centimeter. Well, if I now double those side lengths to 2 by 2, the area actually goes up by a factor of 4. And the reason why that is we'll see that soon enough, is that because it's the distance is what I'm doubling, and the area is basically distance times distance. And so it's essentially going to get multiplied by that scale factor twice. So if the distance goes up by a factor of 2, area goes up by a factor of 4. But again, it's still direct proportionality. As one goes up, the other one goes up. As one goes down, the other one goes down, and so on. So let's apply that to, say, some units. So first of all, let's look at some prefixes of units. Like whenever you come across something like milli means 1,000. Like milliliter is 1,000 liter. Kilo, we often use the word kilo to mean kilograms. Like we'll say, 50 kilos. That means 50 kilograms. But the actual word kilo means 1,000. And that's why you have kilogram means 1,000 grams. But you can also have kilometer, which is 1,000 meters, and so on. And then you have centi being hundreds. We've seen before cent relating to 100. So if you have something like 50 centimeters, we can convert that into 0.5 meters, 500 millimeters. So these units are all directly proportional to one another, because they're kind of like the same, measuring the same thing. Same thing with milliliters. You see, if we're going from milliliters up to liters, You see, we're dividing by a factor of 1,000. And same thing with 1,200 grams. If we want to go to kilograms, we're dividing by a factor of 1,000. If it was going the other way, it would be multiplying by a factor of 1,000. So just be mindful of which one's the bigger unit will then tell you whether or not you have to multiply or divide. And the kilo there indicates it's going to be a factor of 1,000 is what we're multiplying or dividing by. Right. What we just need to look at is when we have things like like compound units like this. So this referring to area because it's a meters squared. So say if I was converting this to centimeters, well, we know there's 100 centimeters to a meter, but then that doesn't mean it's going to be 25 times 100. Because when we substitute the meters for 100 centimeters, well, the 100 is also getting squared. So it's 100 centimeters all being squared. So you get centimeters squared, but you also get a factor of 100 squared. And so this actually comes out to 250,000 centimeters squared. Similarly, if we have something like this, we can substitute, 1 milliliter is basically 1,000th of a liter. The seconds is just staying the same. We're not changing, the time unit here. So we're essentially just dividing by 1,000. And we know this is why, we tend to work in, factors of 10, like a factor of 100 or 1,000, because it allows us to shift the decimal point. Now, this is the beauty of the metric system. So we just shift the decimal point 3 places like that. Final one would be, say, something like this, which would be like a measure of pressure. And say if we wanted to change both units here, so we're changing that meters into centimeters again. So we put 100 centimeters, and the kilograms is being replaced for 1,000 grams. And okay, so now we know the units is going to be grams over centimeters centimeters squared. The 1,000 is just saying 1,000. The 100 is being squared, but you see, because it's kilograms over meters squared, you treat it like, it's just like a fraction, really. So those numbers that are coming out from that is also going to be, a fraction. So you get 1,000 over 100 squared. And 100 squared is what? 10,000. So we're doing 1,000 divided by 10,000. It's essentially you have a net result of divided by 10. So we get 0.32 grams per centimeter squared. So that's how we would substitute for units, which is, a part of proportionality. So they're always going to be, very much directly proportional because they're measuring the same thing just in a different way. Now let's look at inverse proportionality, which is kind of the opposite. So it's as one thing goes up, the other one goes down. So that's what it means essentially by inverse. It's like opposite. So two quantities are said to be inversely proportional. Yeah, if one results in a proportional decrease in the other. So here's an example of, say, if I was traveling 45 kilometers at a speed of 60 kilometers an hour or 30 kilometers an hour, and you see it will either take 45 minutes or an hour and a half. And it kind of makes sense, doesn't it? If I'm traveling faster, it'll take me less time. So as my speed goes up, the time it takes will go down, and vice versa. So that's an example of like an inverse proportionality. So a lot of what we've already seen just still applies. It's just like the reverse way around. So let's look at this example here. So say if we were filling up a swimming pool and it takes 21 hours to fill up that pool at a rate of 12 liters per minute. So now we've been told a blockage has reduced the rate to only 7 liters per minute. How long will it now take to fill the pool? So this is an example of like a proportionality question, because we can't really calculate it directly because we haven't been told how many liters are in the pool. Although we could work that out if we wanted to from this, but we don't really need to. Here it's kind of like with the recipe example, where that's like an example of proportionality when we're trying to go up from a recipe for 4 people up to 6 people, but we're trying to keep all the proportions the same. We look for that scale factor. It's the same thing here. So we're at 12. We was going at 12 liters per minute. Now it's dropped to 7 liters per minute. We want to see, okay, what is that scale factor? Well, we can calculate that in like the way I described by like this. So it's going to be 7 over 12 because that 12, I divide by 12 gets me to 1, times by 7, it will get me up to 7. So times by 7 divided by 12 is the same thing as times by 7 over 12. So that's our scale factor there. That's what, that's the rate of change, the change from 12 to 7. So we can apply the same thing to the 21, but you see before where we multiplied each one by the scale factor, this time we're dividing it because it's inversely proportional. As one goes up, the other one goes down. So here, as the rate of flow is gone down, because we're multiplying it by 7 over 12, that's less than 1, so it's actually, it's reducing it. Now we're going to divide by 7 over 12, which is actually going to make it bigger, because it's essentially the same thing as times it by 12 over 7, which is greater than 1. So that's the important thing to know with inverse proportionality like that, is when you then go to take those proportions, you're going to have to flip that scale factor there, because you need to ensure that they're going in opposite directions. One goes up, the other one goes down, and vice versa. And then we're just calculating the same way we've done before. So you see, we get 21 times 12 on the top divided by 7. Well, that 21 can be divided by 7 to get 3. 3 times 12 gets 36. So that's the end of this lesson on ratio and proportionality. Next time, we're going to move on to like more real world applications of them. So let's finish up with this. Did you know about a special ratio known as the golden ratio? You might have heard of it before, as many uses in fields beyond mathematics. And that's this ratio here, roughly speaking, 1 to 1.618. But not exactly. It's actually this number here. It's an irrational number. So you remember when we talked about irrational numbers before, like pi has this infinite decimal expansion. So this very special ratio is something we see crop up all over the place. And mathematically, it looks like this. You imagine drawing a 1 by 1 square, and then you see that's, on the left there, and then a square then up in the top right, and then bottom right, and so on and so forth. Each one getting smaller and smaller by that ratio. And you see this arc that we're putting through it. It's like a quarter of a circle. You see how it creates this spiral that goes round and round, and it will keep going on forever and forever, just keep getting smaller and smaller. And we see this ratio just appear all over the place. So, like, here's an example. You see it like in nature, in a shell. We see it in flowers, like sunflowers here, like the pattern of the seeds and things like that. You even see it on the big scale, like with galaxies and like the spiral arms of this galaxy, and the separation between them just so happens to follow this ratio. And there's a reason why we see this ratio appearing all sorts of places, because it has this like perfect balance between like structure, strength, and compactness, like efficiency of space, and so on. And so this is something that tends to actually look very nice to us, and that's why it's then often used in things like this, like art and photography. They'll often follow this golden ratio because it will look pleasing to us. You see it like here, in terms of like the relative proportions of different parts of an image. Even companies have used this in designing their logos and so on. So yeah, there's like this psychological element to it. But that's just an interesting fact for you there. Let's leave you here with the takeaways, and I'll see you next time for some more, the second and final lesson on ratios and proportions. Like I said, it's a short topic. I'll see you there.